Welcome to the Deep Dive, where we unpack fascinating research papers and pull out the coolest parts. Today, we're taking a deep dive into the world of shapes. Well, not just any shapes. We're going to be talking about spheres that are almost perfect.
Yeah, and what's even cooler is we're not confined to just the 3 dimensions we're used to. Imagine spheres in 4D, 5D, even 10D, and how mathematicians, like detectives, can actually prove how close those shapes are to being perfectly round.
Our guide for this deep dive is a recent paper by Hunter Stufflebeam and Paul Sweeney Jr. And let me tell you, they've uncovered some pretty amazing things about these almost spheres. But before we get lost in those higher dimensions, let's start with something a little closer to home, a basketball.
Picture that basketball, perfectly round, and imagine spinning it. No matter how you spin it, it always looks the same, right? That's rotational symmetry. Now, hold on to that thought as we take it up a notch.
Because in this paper, we're not just dealing with basketballs. We're talking about shapes that are almost spheres existing in any number of dimensions. It's like asking, what would a basketball look like in a world with 10 different directions? It's enough to make your head spin.
And here's where it gets really interesting. This isn't just some abstract mathematical puzzle. Understanding the shape and curvature of objects, even in higher dimensions, has some very real implications.
Okay, I'm intrigued. Give me an example. What could this kind of math actually be used for?
Well, think about something like GPS. It relies on incredibly precise measurements of the Earth's shape, and not just in 3 dimensions. We need to account for the curvature of space-time itself to make sure your directions are accurate.
Wow, I never thought about it like that. So we've got these almost perfectly round spheres hanging out in multiple dimensions. What's next?
Enter the world of minimal surfaces. Imagine dipping a wire frame into soapy water. The film that forms across the frame will always take the shape with the least possible area. That's a minimal surface.
Like a soap bubble finding the most efficient way to exist.
Exactly. Now, these minimal surfaces play a key role in understanding the shapes of those almost spheres.
So how do mathematicians even begin to prove that a shape in, say, 5 dimensions is close to being a perfect sphere? It's not like we could just hold it in our hands and measure it.
You're right, it's not that simple. But that's where things get really clever. Remember that 2012 proof we mentioned earlier by Marquez and Neves? They gave us a powerful tool to crack open these kinds of problems.
Like the hidden fingerprint idea. But how does their work connect to what Stufflebeam and Sweeney Jr. are doing in this paper? Give us a little background on that.
Well, Marquez and Neves focused on perfectly round spheres in 3 dimensions. They proved that if you find a minimal surface inside that sphere with a specific area, boom, you know for sure that your shape is a perfect sphere, no doubts whatsoever. But Stufflebeam and Sweeney Jr. took it a step further.
So they took this idea of a perfect sphere and said, what if we shake things up a bit? What happens if it's just almost a sphere?
Exactly. It's like taking that perfectly round basketball and, giving it a little dent. It's not perfectly spherical anymore, but it's still pretty close. And that's where this idea of stability comes in.
Okay, so stability is like asking how much we can mess with the shape before it completely loses its almost sphereness.
Right, good.
Yeah.
You got it. Think of it like building a bridge. You need to know how much weight it can handle before it collapses. Same idea here, but instead of weight, we're talking about how much we can tweak the shape before it becomes something completely different.
And that's what makes this whole thing so applicable, right? Because in the real world, nothing is ever perfectly symmetrical.
Precisely. Take those 3D models you mentioned earlier. They're always going to have some degree of imperfection, however small. Understanding stability in this mathematical sense could help us figure out how much imperfection is acceptable before the model, becomes unusable.
That makes a lot of sense. But how do you even go about measuring how close a shape is to being a perfect sphere, especially when we're talking about dimensions we can't even visualize?
Well, that's where Stufflebeam and Sweeney Jr. introduced this really cool concept called MinA. You can think of it like a mathematical tool for measuring roundness, even in those higher dimensions.
It sounds almost like a character from a sci-fi novel. So how does this MinA thing actually work? What makes it so special?
Imagine you're trying to, reshape a piece of clay that's supposed to be a sphere. You might accidentally create some sharp points or weird bumps along the way, right? MinA helps us figure out if, despite those imperfections, the shape is still fundamentally spherical at its core.
So it's kind of like a way to see past the imperfections and get to the heart of the shape, even in higher dimensions.
Exactly. And here's why that's so important. Remember those rigidity theorems, like the one from Marquez and Neves? They gave us a way to prove something was perfectly round. But with MinA, Stufflebeam and Sweeney Jr. are able to explore the much more complex world of shapes that are almost round, and prove that even with imperfections, they can be surprisingly well-behaved.
So are we saying that these almost spheres are way more stable and predictable than we might have thought?
That's exactly what they're finding. And to prove it, they came up with not just one, but 3 new theorems. Let's take a look at theorems A, C, and D in their paper.
Okay, so theorems A, C, and D. What do those actually tell us? Why should our listeners be excited about these?
Well, each of these theorems basically shows that when you have a shape and it's close to being a sphere, it's going to act a lot like a sphere. It's kind of like, if you bend a metal rod just a bit, it's not perfectly straight anymore, but it's still going to mostly behave like a straight rod. These theorems, it's kind of like that, but for shapes and curvature.
So like there's this underlying spherical essence that persists even when the shape's not perfect.
Yeah, exactly. And these theorems, they give us the math tools to actually prove that. Each theorem focuses on something a little different. They use these different types of convergence. You've got your IF, your VIF, your GH, which, might sound complicated, but it's really just like using different ways to measure how similar 2 shapes are.
Like having different lenses to look at the same object.
Yeah, that's a great way to put it. And what we find is these almost spheres, they're surprisingly resilient. They really hold on to their shape in a predictable way.
This has been so interesting. We're talking about higher dimensions, complex math, but there are clear connections to the real world. Where else could this research have an impact?
Oh, tons of places. Think about architecture, designing buildings that need to be super strong but also lightweight. Or how about material science, creating new materials with unique properties? I mean, the possibilities are huge.
It really is amazing to think that something as, seemingly abstract as the shape of an almost sphere could have such a big impact.
It is pretty cool, isn't it?
It really is. This deep dive has really opened my eyes, and I hope our listeners feel the same way. Until next time, keep exploring, because there's always something new to discover. All right, so today we're diving into the deep end. We're going to be talking about the shape of the universe.
Yeah, we're looking at width stability of rotationally symmetric metrics. It's a research paper tackling some pretty big questions like, how does the actual shape of space connect to other measurements, other quantities that we can compute?
Okay, hold on. So we're talking like decoding the universe using math. I'm in. Let's do this. But maybe let's take a step back for a second. What does rotationally symmetric even mean in this context? I'm picturing like planets and pottery wheels, but it's probably a little more complex than that.
Right. So you have the right idea. Take, a basketball, a planet, something that you can spin around, and from every angle it looks the same. That's rotational symmetry.
Okay, that makes sense. And this paper, this rotationally symmetric metrics paper, is looking at spaces with that kind of symmetry.
That's right.
Okay, so spaces, we're already venturing out of my usual 3-dimensional thinking here.
Yeah.
And this is where the whole width thing comes in, right?
Exactly.
But I have a feeling we're not talking about measuring a doorway.
Not exactly, no. So think about like a canyon. The narrowest point between those canyon walls limits how much water can flow through, how big of a, truck can drive through. That's kind of like the width in this sense.
So it's like a bottleneck. It's like the narrowest point that still lets something pass through.
Yeah. It's a measure of size, but not in the typical way, like with a ruler.
Okay, I think I'm starting to get it. But why is this width idea so important? Why go through all this trouble to figure it out?
So this paper is trying to answer a question that's been bothering mathematicians for a while now. If a space is rotationally symmetric and has a certain width, is it similar to a sphere?
Wait, hold on. Are we saying that by studying the width of these spaces, we could figure out if our universe is shaped like a giant sphere? Because that is wild.
It's a big question, yeah. And this paper is a step towards answering that. They're really pushing the boundaries of geometric analysis.
I'm already feeling my brain bend, and we're just getting started. So how do you even begin to tackle a question this complex? What tools are these mathematicians using to study the width of something that we can't even picture?
Yeah, that's the really cool part. A lot of the typical tools that we use in math, they kind of break down when you go beyond 3 dimensions. But this is where that symmetry is so important.
Okay, so the rotational symmetry gives us a way in.
Exactly. Yeah, it's like having a map with a grid system. It lets us use these special coordinate systems like longitude and latitude to navigate these really complex shapes.
So we're imposing order on this abstract, multidimensional world.
Yeah, you could think of it that way.
That's really clever. And by doing that, does it make the math a little easier?
It does, yeah. Because we can use tools from this field called PDEs, partial differential equations.
PDEs, that like the math of ripples in a pond?
That's one way to think about it, yeah. It's basically the math of how things change.
Okay, so they've got their coordinate system, their ripple analyzing equations.
Right.
What's next? Do they just like dive headfirst into this really complex math?
They do, but it's not just a simple calculation. To prove their idea, they had to get creative, and their approach is actually really elegant, but it involves being really precise with the measurements and things like that.
Okay, you've got to elaborate on that. What exactly did they do? How do you measure the width of something we can't even picture?
So they start by using these special coordinates, the ones that are only possible because of the rotational symmetry.
Right.
And then they focus on measuring certain geometric properties within those coordinates. Imagine trying to measure the Earth's circumference, but do it on a much weirder, more complex shape.
Okay, I'm starting to understand why this is cutting-edge stuff.
Yeah, and here's where it gets really interesting. They actually need to use two different coordinate systems to fully understand the entire space.
Two maps for one space. This just gets even more mind-boggling. Why two? What's so different about these systems?
That's a great question, and it leads us to this really fascinating part of the paper, the idea of a bad set.
A bad set.
Uh-oh.
It's basically a region within these spaces where things get a little messy, a little unpredictable.
Okay, so is this like a wrinkle in the fabric of space-time?
You can think of it that way. Imagine you have a piece of silk, and it's mostly smooth, but then there's this one weird, rough patch.
And that's our bad set.
Exactly.
So does that mean these perfectly symmetrical spaces are doomed to have these weird flaws?
Well, that's the thing. The researchers found a way to control the size of this bad set, so it doesn't completely throw off their calculations.
Okay, so it's like that rough patch on the silk. It might be there, but it doesn't mean the whole thing unravels. That's a great way to put it.
Okay, so we've got our symmetrical spaces, our mathematical maps, and even our bad set. But I'm still curious about this whole convergence to a sphere idea. What does that actually mean? Are these spaces literally morphing into spheres before our very eyes? Are these spaces literally morphing into spheres before our very eyes?
Not morphing exactly, more like, imagine a sculptor. They start with this rough block of clay, right? And as they mold it, as they shape it, it starts to resemble a sphere.
Okay, I can picture that.
But there might be some, bumps and imperfections along the way.
Right.
This paper is saying that even with those imperfections, those bad sets we talked about, these spaces under the right conditions, they get closer and closer to being a perfect sphere.
So the more we kind of mold these spaces, mathematically speaking, the closer they get to that perfect sphere.
Exactly. We're talking about abstract mathematical spaces here, not physical clay or anything.
Right, of course.
But the principle is similar. The paper is a proof, a really rigorous proof, that these spaces, with their width and their symmetry, they can become unbelievably close to a perfect sphere.
Okay, my mind is officially blown. We started with these abstract shapes in multiple dimensions, threw in some width, a dash of symmetry, and boom, we're approaching a perfect sphere. It feels like mathematical magic almost.
It's pretty amazing stuff. And here's the thing. This isn't just some theoretical exercise.
Oh.
This research has real implications for how we understand the universe around us.
Wait, really? How does this high-level math connect to the real world?
Well, think about cosmology, the study of the universe as a whole. One of the biggest questions in cosmology is, what is the shape of the universe?
Right, I've heard about that.
Is it flat? Is it curved like a sphere? Or is it something else entirely?
And you're saying this research, this width research, might actually help answer that.
It's a piece of the puzzle, yeah. By developing these tools, these really powerful tools to analyze the shape of spaces, even spaces with more dimensions than we can really picture. We're gaining this deeper understanding of geometry at all scales, potentially even the cosmic scale.
So we're not just talking about the shape of some theoretical space. We're talking about the shape of the universe itself. That's incredible. But how can we be sure? How do we know that the rules of geometry, the rules that we're talking about here, actually apply to something as vast and complex as the universe?
That is the million-dollar question. It's something that physicists and mathematicians have been wrestling with for centuries. But here's the thing. Time and time again, we find that the universe seems to follow these elegant, often surprising mathematical rules.
So it's like math is the language of the universe,
Yeah.
and we're just starting to figure out how to read it.
Exactly. And this paper, it's like we're discovering a new phrase, a new sentence in that cosmic language.
I love that. That's why I love a good deep dive. We started with this one research paper about the width of symmetrical spaces, and now we're talking about the shape of the universe and the language of reality.
And we're not done yet. This paper is groundbreaking, but it's just one step on a much longer journey.
Okay, you've definitely got me hooked. What's next? What are the big unanswered questions that this research opens up?
Well, one question that I find particularly interesting is this. If we can prove that these spaces with certain properties always converge toward a sphere, even with these bad sets we've been discussing, could we find a way to smooth out those bad sets?
Smooth out. What do you mean by that?
Like, imagine if we could take that sculptor's clay and find a way to make it perfectly smooth, even in the spots where it was rough or uneven before.
You're saying like mathematically iron out the wrinkles.
Precisely.
That's some next level math. But what would that even tell us? Why is it so important to chase after these perfectly symmetrical, bad set-free spaces?
Because it could unlock entirely new mathematical concepts and theories. Think of it this way. Our current understanding of geometry, it's built on certain assumptions, certain rules.
All right.
But what if those rules are just a small part of a much larger, more intricate system?
So by smoothing out those bad sets, we might actually stumble upon entirely new rules of geometry.
Exactly.
Rules that could completely change how we understand space and shape.
It's like we've been exploring this continent. We've mapped out its coastlines, its mountains, its rivers.
Right.
But this research, this idea of taming the bad sets, it's like discovering a hidden passage to a whole new continent, one we never even knew existed.
I love how one research paper can open up so many possibilities.
Me too.
It's like we zoomed in on this one specific concept, width, and it gave us this telescope to see the entire universe of geometry in a whole new light.
And that's what makes this field so captivating. Every answer leads to more questions. Every discovery opens up these new avenues for exploration.
Like we're always on the edge of something groundbreaking.
Exactly.
Well, I think we've all earned ourselves a PhD in width today.
I'd say so.
Though I have a feeling we've only just scratched the surface.
Oh, absolutely.
And that's the beauty of it, isn't it? There's always more to learn, more to uncover, more to explore. But for now, we've reached the end of our deep dive.
It's been quite a journey.
We journeyed from the width of abstract spaces to the shape of the universe itself. And I don't know about you, but my brain is buzzing.
As always.
To our listeners out there. Thank you for joining us on this incredible adventure. We hope this deep dive has sparked your curiosity and left you with a sense of wonder about the hidden mathematical language of our universe. Keep exploring, keep asking questions, and keep diving deep. We'll see you in the next episode of The Deep Dive.
It's like we're always on the edge of something groundbreaking.
Well, I think we've all earned ourselves a PhD in width today.
I'd say so.
Though I have a feeling we've only just scratched the surface.
Oh, absolutely.
And that's the beauty of it, isn't it? There's always more to learn, more to uncover, more to explore. But for now, we've reached the end of our deep dive.
It's been quite a journey.
We journeyed from the width of abstract spaces to the shape of the universe itself. And I don't know about you, but my brain is buzzing.
As always.
To our listeners out there, thank you for joining us on this incredible adventure. We hope this deep dive has sparked your curiosity and left you with a sense of wonder about the hidden mathematical language of our universe. Keep exploring, keep asking questions, and keep diving deep. We'll see you in the next episode of The Deep Dive.
Hey there, Deep Dive ready. Buckle up, because today we're diving headfirst into the wild world of Riemannian geometry.
Sounds intimidating.
It's actually way cooler than it sounds. Forget endless equations, we're talking about shapes and sizes, but on a cosmic level. Like, imagine planets, black holes, even the entire universe.
That's a bit of a jump.
Well, you guys sent in this seriously dense research paper called With Stability of Rotationally Symmetric Metrics.
Catchy title.
Right, and we're here to break it down, make it a little more, digestible.
Sounds delicious.
We'll uncover all the good stuff, the aha moments that make this paper so fascinating.
I do love a good aha moment.
And lucky for us, I've got an expert right here who can make even the most complex math feel like an episode of, well, your favorite show.
It's all about asking the right questions. And this paper, it dives into some seriously mind-bending ones about how shapes can change.
Okay, so let's unpack this rotationally symmetric metrics. Can you give us a simple way to picture that?
Picture this: a perfectly round orange
Okay, I'm with you.
or a spinning top frozen in time.
Got it.
They both have this property of looking the same no matter how you rotate them.
So symmetry, basically.
Exactly. And what this paper wants to figure out is, what if you slightly warp these perfectly symmetrical objects? How much would their fundamental shape actually change?
So, like, how much can you poke a rubber ball before it's no longer a ball, but some weird dented thing?
That's the idea of stability in mathematics. And
Yeah.
guess what? This paper explores if some shapes are more resistant to change than others.
Okay, so we're already talking about black holes, and it's only 5 minutes in. This is amazing. But how do we even measure the stability of a shape, especially something as mind-boggling as a black hole?
That's where it gets really interesting. They use something called canonical sweepouts.
Canonical what now?
Stay with me. Imagine slicing that perfect orange at all different angles to analyze it.
Okay, I can picture that.
That's essentially what a sweepout does. It helps us measure the object systematically, even if it gets warped or distorted.
And the width is all about finding the smallest possible slice as we sweep through, right? Like if we're thinking about our orange, the smallest slice would be right through its center.
You got it. And here's where it gets mind-blowing. This paper proves a width rigidity theorem, which basically means that for certain objects, just knowing that smallest slice, their width, tells us everything about them.
So we're talking about understanding the entire shape of something as complex as a black hole just by knowing its width. That's a seriously powerful concept. But how do we even begin to test the limits of this stability? How much can we poke these shapes before they, well, lose their cool?
Well, that's where scalar curvature comes into play, and it's a pretty wild ride.
Scalar curvature, huh? So are we talking like the edges of a shape?
Not exactly. It's more about how much a surface bends at a particular point.
Okay, so give us a visual, because my brain's not quite getting there yet.
All right, picture a bowling ball sitting on a trampoline, really stretching things out.
Okay, I can see it.
That's high curvature.
Hmm.
Now imagine a feather on that same trampoline, barely making a dent.
Low curvature. Got it.
This paper asks, how much can you change the curvature of a shape, like our orange, or even a black hole, before it basically falls apart?
I'm starting to see how this all connects. So we're essentially poking the trampoline with different amounts of force to see how much the shape changes and if it can, like, bounce back.
Exactly. And what they found in this paper, using some seriously hardcore math, is that if you poke too hard, meaning you lower the scalar curvature too much, those perfectly symmetrical shapes, they become unstable.
So there's a tipping point where it's no longer that stable shape we started with. But this still seems kind of theoretical. We're talking about poking imaginary shapes in math land, right? How does any of this apply to the real world? Like, why should we care about the width of a black hole?
Because that's where things get really, really exciting. See, Riemannian geometry, this whole world of shapes and curvature, it's not just stuck in textbooks. It helps us understand some of the biggest mysteries in the universe.
Wait, are we going from oranges to the entire universe right now?
Fasten your seatbelts. Remember that trampoline analogy? Well, imagine the universe itself is like a giant trampoline, this fabric of space-time.
Okay, my mind is trying to keep up.
Now think about the forces that could be stretching or compressing that fabric. Things like dark matter and dark energy, stuff we barely even understand. Those forces are changing the curvature of the universe.
Whoa, hold on. So this paper is telling us how much the universe can be, like, stretched or poked before it might. What happens then?
Well, that's the million-dollar question, isn't it? It's like this paper gives us a new ruler to measure just how stable the universe is.
That is mind-blowing. Are we talking, like, potential applications for understanding the Big Bang or something?
Potentially. It's all connected. But here's a more concrete example.
Yeah.
Black holes.
Okay, bring us back down to Earth, or at least try to.
Imagine a place where gravity is so strong, it literally warps the fabric of space-time, causing it to curve infinitely inward.
Infinite curvature. My brain just glitched.
Think about our bowling ball on the trampoline, but instead of just stretching the fabric, it tears a hole straight through it.
Yeah.
That's what we think happens at the singularity of a black hole.
So we're saying that by understanding these principles of stability and curvature, we might be able to unlock, like, the secrets hidden inside these cosmic monsters.
You're getting it. It's about using these mathematical tools to probe the most extreme environments in the universe.
So we're on the verge of understanding some of the most mind-blowing things in the universe just by thinking about the shape of an orange. This is unbelievable. It's just incredible how this paper connects these massive, almost impossible to imagine concepts with something as simple as the shape of an orange.
It's like a hidden code, right?
Exactly, like we're unlocking the universe's secrets.
And this paper, it gives us a whole new way to study these crazy cosmic phenomena.
Totally.
The more we understand these basic math principles, the closer we get to figuring out the universe's greatest mysteries.
You know, when we started this deep dive, I definitely didn't think we'd be talking about the fate of the universe.
It's pretty wild, right?
It really goes to show that even in the most abstract parts of math, there's still potential for incredible discoveries.
That's the beauty of mathematics, isn't it?
Cool.
It's like this universal language that underpins everything around us.
It's true.
And papers like this one, I mean, they might seem impossible to understand at first,
Oh, yeah, for sure.
but they can actually completely change how we understand the universe.
And our place in it, no less.
Exactly.
So for our listeners out there, if they only remember one thing from this deep dive, what would it be?
Ooh, that's a good question.
There's a lot to unpack here.
Right. I think it's never underestimate the power of a simple question.
It all starts with a question, huh?
Exactly. Who would have thought that thinking about the stability of shapes, like an orange, could lead us to insights about the universe?
It's kind of poetic when you think about it.
It really is. It reminds us that being curious and really wanting to learn can open up these incredible possibilities.
I love that. A huge thank you to you for taking us on this mind-bending journey.
It was my pleasure.
And to our awesome listeners, keep those brains buzzing. Keep asking those big questions, and we'll catch you on our next deep dive into the unknown. Ever really stop to think about, like, what actually makes a sphere a sphere?
I mean, we see them everywhere, right? Like a
Oh.
basketball or like a globe, round.
Right.
But what if I told you there's this whole area of math, like digging into the idea of almost spheres,
Okay.
shapes that are like so close to being spheres,
Yeah.
but just a little off.
Uh-huh.
It'd be like taking that basketball and like poking it,
Okay.
giving it a tiny dent or warping it just a bit.
Yeah.
That's what we're diving into today.
Okay.
A research paper called With Stability of Rotationally Symmetric Metrics.
It's all about, like, pushing the limits of what makes a sphere a sphere.
And trust me,
The results are way more interesting than staring at a boring old round ball.
it's true. This isn't about like those imperfections you can see just by looking at something.
Right.
It's deeper than that.
Yeah.
We're diving into the underlying math here,
Okay.
really exploring what makes a shape what it is.
And that's where things get really interesting, right?
Evidently.
Because it's not just about looking similar anymore.
Right.
We're talking about the mathematical properties that define these almost spheres.
Exactly. One of the key properties they focus on is something called scalar curvature.
Okay.
It's essentially a way to measure how much a space is curved at any given point.
So like a basketball would have a certain scalar curvature,
Exactly.
and like a donut with its hole and curves would have a totally different one.
Exactly. Each shape has its own unique curvature.
Okay. I think I get that. But how do you actually, like, measure something like curvature in all these different shapes?
So this is where things get even more interesting.
Yeah.
This paper uses a concept called width.
Okay.
Now, forget about the usual idea of width here. We're talking about something very specific.
Okay.
Imagine slicing through a sphere
Huh?
at all different angles.
Right.
The width is the smallest possible cross-section you could make.
So it's like finding the narrowest neck of the sphere,
You got it.
no matter how you twist and turn it.
And what's amazing is that there's a proven link between this width and the scalar curvature.
Okay.
If a shape has a specific width and its scalar curvature meets certain conditions, it must be a perfect sphere, no exceptions.
So no wiggle room whatsoever.
Mathematicians call this a rigidity theorem, like a hard and fast rule.
Got it. But this paper doesn't stop at just proving this for perfect spheres, does it? It pushes further right.
They're asking what happens when the conditions for a perfect sphere are almost met.
The almost part.
Yes. Imagine you take a ball of clay
Uh-huh.
and you just kind of poke it gently. You dent it just slightly. How much can you deform it and still have something that mathematically behaves very close to a sphere? That's where the stability part comes in.
So it's like a spectrum.
Exactly.
On one end, you've got that perfectly rigid sphere.
Yes.
And then on the other end, you've like squashed the clay so much it's unrecognizable.
And they're trying to figure out that fuzzy boundary in between.
Precisely. And to measure this closeness, they use some pretty high-level math. They found ways to quantify how much these almost spheres differ from perfect spheres.
Okay.
Even in dimensions higher than we can visualize.
Higher dimensions. Okay, now we're getting into some seriously mind-bending territory.
But before we journey into the fourth dimension and beyond, can you give us a concrete example of how this almost sphere idea works in our normal three-dimensional world?
Of course. One example they give is a shape that looks like a string of spheres all linked together.
Okay.
Even though it's not a single smooth sphere,
Right.
its curvature and width are so close to the ideal values that mathematically it behaves almost identically to a perfect sphere.
So it's not even just about whether something looks like a sphere.
It's about whether it acts like one.
Right.
Mathematically.
Exactly.
Even if it's kind of a wonky shape.
Yeah. And that's where this paper gets even more interesting.
Okay.
Because they didn't just show that these almost spheres, they exist.
Huh.
They actually found,
They uncovered some of their properties.
Okay.
For example, they found that even if you slightly dent or warp a sphere, it can still retain certain vibrational qualities.
Wait, you're telling me...
So you're saying if you have something that's almost a sphere,
Yeah.
even if it's dented,
it could still ring like a bell.
Oh.
Almost the same way a perfect sphere would.
it's a little more complicated than that, but you're on the right track.
Okay.
It's like these almost spheres.
Yeah.
They hold on to this kind of ghostly echo of their perfect form, mathematically speaking.
That's wild.
So finding out that a dented tuning fork can still almost hit that perfect note.
But why does any of this matter?
Why are mathematicians so fascinated by this idea of almost spheres?
Does this have any impact outside of theoretical math?
Absolutely. Remember that scalar curvature we talked about?
Yeah.
Well, it's not just some abstract concept. It plays a key role in how we understand the universe.
The universe.
Like with stars and planets.
Exactly. The curvature of space-time, the very fabric of the universe, is influenced by massive objects.
Like stars and black holes.
Right.
And this research gives us new tools
to study and model those incredibly complex phenomena.
Okay. So we're talking cosmic level implications here.
But what about closer to home?
Sure.
Any practical applications of this research?
As a matter of fact, yes.
Okay.
Think about materials, science, engineering.
A perfect sphere is incredibly strong for its weight because of its uniform curvature.
That's why they make water towers spherical.
Right.
To distribute the weight evenly.
Now imagine understanding how slight deviations from perfect sphericity affect a structure's strength and stability.
Right.
That could lead to new materials.
Okay.
Stronger materials, lighter materials.
So you're saying
By understanding the math behind these almost spheres.
we might be able to build things more efficiently.
Exactly.
Using less material.
But still retaining the strength.
Precisely.
Yeah.
And that's really just scratching the surface.
Wow.
This research has potential in nanotechnology, computer graphics.
Okay, I am officially fascinated by these almost spheres. But you mentioned higher dimensions earlier.
Yeah.
And I gotta be honest.
My brain still can't quite picture a four-dimensional almost sphere.
It's true. Our brains aren't really wired to visualize higher dimensions directly.
Right.
But we can use analogies to kind of wrap our minds around it.
Okay.
Imagine a flat, two-dimensional world.
Okay.
Like a piece of paper.
Gotcha.
Now, draw a circle on that paper.
Uh-huh.
To us, looking down from the third dimension, it's a flat, enclosed shape.
Right.
But imagine an ant living on that paper, confined to that circle's edge.
You'd only be able to travel along that round path, right?
Exactly. To that ant, the circle's edge would feel like a one-dimensional line.
Okay.
We perceive the extra dimension.
Because we can step outside the circle and see it from above.
Right. We have a different perspective.
Similarly, these almost spheres in higher dimensions might have properties, implications.
That we can't grasp visually, but the math lets us explore them.
So what you're saying is these shapes, even though we can't picture them,
could be the key to unlocking
even bigger things about the universe.
Things we haven't even imagined yet.
It really is a trip, right?
Yeah.
It makes you wonder,
Yeah.
what do we even call perfect anymore? you know?
Right.
Maybe it's the imperfections that actually make things interesting,
It's true.
mathematically speaking.
Okay, so before we go too far down this rabbit hole of like...
Almost shapes.
Right.
Can you, bring us back to the main point?
Sure.
What's, the big takeaway from this research?
What should people be thinking about after listening to this?
Yeah. What do we really want our listeners to walk away with?
I think the key takeaway here is that math isn't just about formulas and equations. It's more than that. It's like a language.
Okay.
A way to understand how things work at the most fundamental level.
Right.
From tiny particles
To giant cosmic structures.
Uh-huh.
And sometimes the most amazing discoveries.
happen when we start questioning what we think we know about shapes, about dimensions.
I love that. It's like this research is telling us to
Embrace the almost
Yeah.
in our search for knowledge, because sometimes those imperfections, those almost perfect shapes.
they can show us even more
Yeah.
than we thought we knew.
Absolutely. And that kind of brings us to one final thought.
Okay.
We've been talking about how hard it is
Yeah.
to picture these higher dimensional almost spheres. Right.
It hurts my brain.
But what if instead of trying to fit them into our three-dimensional understanding,
Yeah.
what if we tried to imagine experiencing those higher dimensions ourselves?
Okay. Now we're talking about some next level stuff.
Like imagine a being that can perceive 4 or 5 or even more dimensions.
Okay.
How would they see an almost sphere in that kind of space?
Right.
Would it even look like anything we can comprehend?
Right.
Or would it be something totally alien to us?
It's a question that's just
It really makes you think.
blows your mind wide open.
And it makes you wonder
Yeah.
what other mathematical mysteries are out there,
Right.
hidden in plain sight.
Just waiting for us to
Develop the tools.
and the imagination to see them. That's a perfect place to wrap up. So, listeners, if you're ready to go on your own mathematical adventure,
and learn more about the stuff we talked about today.
yeah, definitely check out the book, The Shape of Space by Jeffrey Weeks.
Oh, yeah. That's a good one.
It's really accessible. A great intro to these mind-bending concepts.
It really is. We'll link it in the show notes for you.
So that's it for this deep dive into the world of almost spheres
Thanks for joining us.
as we explored those edges of math
And learned that sometimes it's the imperfections.
that really make things interesting.
Well said. Until next time.
Ever try to figure out the exact shape of something just by touch? Like you can't see it, you're just feeling around?
Uh-huh.
Now imagine trying to do that, but for shapes in more dimensions than you can even picture in your head.
Okay.
That's the kind of challenge that these mathematicians are tackling in this paper that we're diving into today, with stability of rotationally symmetric metrics.
Wow. Yeah, that's quite a mouthful.
It is a mouthful.
Really gets to the heart of what we're talking about here.
It really does. And this paper is really honing in on this idea of stability in geometry.
Yeah.
How can we be sure that a shape is truly close to, say, a perfect sphere, even if it's got some bumps or dents,
Right.
especially as we go to these higher dimensions.
Exactly. And that's actually where this idea of width comes into play. But not width as you and I might typically think of it. It's
Yeah.
not just like measuring across something.
Right.
It's really about understanding a fundamental property that's encoded within the shape itself.
Okay, so let's unpack that a little bit.
Yeah.
So it sounds kind of like those optical illusions where it's you have to look at it a certain way to see the hidden image or whatever.
In a way, yes. Think about slicing an orange
Okay.
at every possible angle.
Okay.
The widest slice that you could possibly make, that maximum diameter. That's conceptually similar to what mathematicians are looking at,
Oh.
with much more complex shapes.
Okay.
And in 3 dimensions, they use something called the Simon-Smith width,
Okay.
which is often shortened to just WSSg.
WSSg, got it. So finding this widest slice, this WSSg, we're getting a little peek behind the curtain of the shape's true nature.
Precisely. And this isn't just a static measurement. It's something that actually reveals how stable a shape is.
Huh.
So if the width stays relatively constant, even when we slightly distort the shape,
Yeah.
we know that it's very stable, very much like a sphere.
So like a basketball, even if it's not perfectly inflated, it's still going to hold its basic form pretty well.
Exactly.
Yeah.
And the paper really highlights that this idea of width as this indicator of stability,
Yeah.
it becomes even more critical when we start to go beyond 3 dimensions.
Okay.
When we start talking about shapes in 4, 5, 6 dimensions, things
Yeah.
get a lot more complex.
Okay.
And we need different tools to really probe and understand those shapes.
And that's where this MinA comes in, right?
Yeah.
What is MinA in this context?
So think of MinA as an extension of that Simon Smith width that we were talking about,
Right.
specifically designed to handle these complexities of higher dimensions.
Sure.
You see, WSSg, it works great for three-dimensional shapes,
Uh-huh.
but it doesn't quite translate to these higher dimensional spaces. MinA allows mathematicians to essentially apply these similar principles to these more abstract forms.
Okay, this is starting to make a little more sense to me now.
Good.
I'm starting to see why this might be important.
Yeah.
Even beyond just like the world of pure mathematics. Because if we're talking about like trying to understand the universe and we're working with Einstein's ideas of space-time and all that, we need a way to analyze these concepts mathematically.
And that's a very astute observation, and you're right, because Einstein's theory of general relativity, that's exactly what it does.
Right.
It uses these types of abstract shapes
Right.
to describe the very fabric of the universe.
Wow.
So understanding their properties like stability
Yeah.
could have huge implications for cosmology.
Really big.
Yeah.
So if we're talking about the universe as potentially being shaped like one of these abstract higher dimensional shapes, how do we even begin to like study its stability?
Yeah, that's one of the really remarkable things about this paper.
Okay.
They focused on a very specific type of shape.
Okay.
One with rotational symmetry.
Yep.
So you can think about it like a spinning top.
Okay.
To understand its overall form, you only need to analyze a single slice.
Oh, that's pretty elegant.
Precisely. Focus on the essential, cut through the noise.
Yeah.
And by focusing on these rotationally symmetric shapes,
Okay.
the mathematicians were able to establish this direct link between the shape's width and how closely it resembles a perfect sphere.
Okay, so the greater the width, the closer it is to being a sphere, even in these higher dimensions.
Exactly. It's like having a powerful new tool determine the width, and you gain all these crucial insights into the shape's overall geometry, especially how close it is to a sphere.
It sounds almost too good to be true.
Right.
Like mathematicians have been grappling with these questions for centuries.
Yeah.
And this paper gives them a shortcut.
It's definitely a significant step forward.
Wow.
And to compare different shapes, to see how closely they align.
Yeah.
They use a concept called, are you ready for this one? Cheeger-Gromov convergence.
I feel like I need to go back to school.
Yeah, it's a mouthful.
Can we break that down a little?
Sure.
What is that?
It's all about quantifying similarity between shapes.
Okay.
Imagine you're trying to see how well two puzzle pieces fit together.
Yep.
Cheeger-Gromov convergence provides a way to measure how closely one shape, even the slightly distorted one, approaches another one, like our ideal sphere.
So it's like, how much do those puzzle pieces overlap?
You got it.
Okay.
And the more they overlap, the more confident we can be that that shape is inherently stable.
Okay.
Even with these minor deviations from perfect symmetry.
This is really remarkable stuff.
It is.
And to think this is all happening in like this world of abstract mathematics.
It's amazing what people are doing.
It really is.
Just with their minds.
Makes you wonder what other like hidden truths are out there.
Oh, I'm sure there are more.
That we just haven't even like scratched the surface of.
And it's important to remember that while this paper focuses on shapes with rotational symmetry, that's just one piece of the puzzle. There's a whole universe of shapes out there.
Oh, I'm sure.
In countless dimensions.
Wow.
With their own like unique properties and behaviors.
Yeah, and who knows how those behave.
Exactly.
It's really kind of mind-blowing to think about.
It is. It
like,
is.
Do those same principles of width and stability apply to those shapes as well?
That's the question, isn't it?
Yeah.
That's what makes this so exciting.
It's like we've just opened the door to this whole new like realm of mathematical inquiry.
Exactly. This research doesn't just answer questions.
Right.
It opens up entirely new avenues of investigation.
Wow.
It compels us to ask.
Yeah.
Okay, what if we apply these concepts to different types of shapes?
Yeah.
What about shapes with different kinds of symmetries?
Uh-huh.
What about ones that have no symmetry at all?
Wow, yeah.
Do these principles still hold true?
It's a lot to consider.
It is.
So what you're saying is this paper isn't like a destination.
No.
It's more like a launching pad.
Exactly.
For even more research.
And it's exciting to think about where this new understanding of shape and stability might lead us.
Yeah, where could it lead?
Perhaps it holds the key to unlocking even deeper mysteries of the cosmos.
The cosmos, yeah.
Yeah.
See, I'm picturing all these shapes.
I know, me too.
Like, as we're talking about them.
It's hard not to.
It would be so cool to actually, like, see them. Like, witness their transformations and understand their properties, but visually.
Absolutely.
Like, is that even possible?
Well, imagine an animation
Okay.
that shows a slightly dented sphere.
Yeah.
And it's gradually smoothing out, approaching this perfect roundness.
Okay.
Or a series of circles expanding and contracting to illustrate the concept of width in this dynamic way.
So kind of like those old spirograph drawings.
A fantastic analogy.
Creating these intricate patterns with like expanding and overlapping circles.
Exactly. And in fact, the paper describes something called a canonical sweepout, which is conceptually very similar to what you're describing.
Okay.
They essentially create a series of progressively larger circles that eventually converge back down, outlining the shape in question.
Oh, okay.
It's a really powerful way to visualize these complex forms.
So that canonical sweepout could be a really useful tool for understanding how these shapes behave.
Absolutely.
How they relate to that concept of width and how we measure their stability.
Precisely. It gives us this framework for analyzing and visualizing these shapes even in higher dimensions.
Okay.
And by exploring these visualizations, we can start to gain like a deeper, more intuitive understanding of the math that's really at play here.
So we're taking this incredibly complex mathematical research and we're finding ways to make it more accessible. Even beautiful.
Exactly, because
to do these visual representations.
Ultimately, mathematics is more than just equations and proofs.
It's true.
It's about uncovering these elegant patterns and structures that underpin our universe.
Finding the poetry hidden in the numbers.
I like that.
Yeah.
That's a good one.
Okay, but before we get too lost in the beauty of it all, let's bring it back down to earth a little bit.
Okay.
So we've gone on this journey, this real deep dive.
Yeah, we really have.
Into some pretty abstract ideas here, you know, exploring the geometry of these shapes that are really hard to wrap your head around.
Yeah, venturing into the unknown.
So as we kind of come back down to earth a little, what would you say, like, what's the one thing to take away from all this? What's the nugget of wisdom we can carry with us?
Well, I think this paper gives us this powerful new lens to understand the relationship between a shape's structure and its stability, especially as we move into those mind-boggling higher dimensions.
Right.
You know, it shows us that even incredibly complex geometric objects, they can be understood if we know where to look.
If we know how to look for it.
Exactly.
It's like we've been given these special glasses that allow us to see the underlying framework of these crazy shapes.
Exactly.
See the elegance in the complexity.
I like that.
And even though this research was on this specific kind of shape, you know, these rotationally symmetric ones.
Yeah.
It opens up like so many possibilities.
It does.
What about the shapes that have different symmetries? Or like, what about shapes that have no symmetry at all?
Right. Are they bound by the same rules?
It's exciting, and it's also kind of like, oh my gosh, it's almost overwhelming.
Yeah, you could say that.
Like we're really just scratching the surface.
Absolutely, and that's what makes this so fascinating.
Yeah.
Because this paper it's a testament
Okay.
to the power of doing this kind of mathematical inquiry.
Yeah.
It shows us there's still so much out there to discover.
So much we don't know.
About these really fundamental concepts, like shape and space.
Like, for someone listening who's maybe not a mathematician, but is, like, fascinated by the universe and all its, like, strangeness and wonder.
Sure.
What would you say is the most mind-blowing thing about this research?
Well, for me, it's really the idea that the universe itself, like the one we exist in and experience, might be just one of many.
Whoa.
Each with its own unique geometry.
Okay.
Each with its own rules governing its shape, its evolution.
Wow.
Yeah.
So, like, there could be a universe out there that's shaped like a donut.
It's possible, right?
Or a pretzel, or, like, something we haven't even thought of.
Something our minds can't even comprehend.
Wow.
That's what's so exciting about it.
That is pretty amazing.
It really is.
Well, we've covered a lot in this deep dive.
I'd say so.
We've gone from, like, the very basic idea of a shape all the way to the possibility of, like, infinite universes.
Yeah.
If you're interested in learning more about this, you know, maybe seeing some of these shapes, like, visually represented.
Yeah, there are some great resources out there.
Definitely check those out because it can really help you understand these ideas.
We could all click.
And who knows?
Yeah.
Maybe this deep dive will spark your own, like, journey into, like, mathematical exploration.
I hope so.
Thanks for joining us.